Well, tonight we'll have some fun with surfaces. Call from last time. Surface integral. Of a function z equals f of x, y. I thought of this like a density function, f of x, y, z, excuse me. Over surface, I don't remember if I use f and g or g and f. All right, over a surface, z equals g of x, y. I think this is the way I wrote it last time. Was this, and so you're thinking of this as the surface. Have some region, and we'll give this surface a name sigma. Think of this as a density function, and so I've got a function of z equals g of x, y up here. Sitting over some down here R. And at each point, the density function is f of x, y, z. So we want to find the mass of this curved surface. We said this was the integral. And we could take a double integral over the region of projection here of f of x, y, and then z is equal to g of x, y. So I didn't write it this way, but we could write, let's x, y, g of x, y in order to evaluate the function on the surface times the square root of the g dx squared plus the g dy squared plus 1 dA, evaluated the surface integral. We can do an example of that here, our equation 1. And so you're thinking of this as ds, and you can write this then for brief notation as the double integral over the surface sigma of f of x, y, z ds has this evaluation scheme. You can take the double integral because of the way we define this. And this was gotten by taking the limit of the sum of all those little tangent planes times the density function, if you like, f of x, y, z. So this notation will mean that limit of the sum that can be evaluated this way. Here's an example, and we need to do one more. And then when I contrast it with one more type of surface integral, just like you could do a scalar line integral or a vector line integral, you can do a scalar surface integral or a vector surface integral also. And in this one, this is the scalar case, you put in a scalar function. So here's a problem to evaluate the double integral over the surface, y squared z squared ds, given ds, given that s has the equation z equals square root x squared plus y squared, and it's over the domain that squeezes us between the planes z equals 1 and z equals 2. We'll go ahead and evaluate that one. So this would be like a surface that at each point has density y squared, z squared, and you integrate it. And what does the surface look like? What does that surface look like? This is an example out of the book, actually, this one. Yeah, oh, good. Yeah, it's really good. Yeah, I'm going to miss you in class tonight. All right, z squared, by squaring it, we can write this equivalently as z squared equals x squared plus y squared with one restriction, right? Since this was the non-negative number that has this square, we have to restrict to z greater than or equal to 0. It's a half cone. by its equation, z equals x squared over a squared plus y squared over b squared, is an elliptic cone. When a equals b like this, it's a circular cone, so this is like half an hourglass. It looks like this. Now I'm going to restrict myself to be between z equals 1, this horizontal plane that intersects this in a circle, and yeah, how big a help it is to be able to draw these things. Z equals 2 in this plane that intersects it in another circle, since it's a circular cone. So we're integrating over this surface between those two planes, part of the half cone. All that sigma. And we can find the mass of that little frustum from a rocket or something, and if it has this mass at each point, y, z, x, y, z. How do we evaluate it? We go by 1, right? We say this is equal to the double integral over the region of projection below it. Maybe I should put that here, where, I drew it. All right. You take where, what is the region below it? You have to project this down. Well, since it's a horizontal circle, it projects down to a circle. This is a horizontal circle, projects down to a circle. So the region is evidently an annulus, right? A washer shape. There it is. And how do we find what that is? Well, we need to find the intersection here of z equals 2 with z equals this, right? We're intersecting the surface in this plane. And so we put the two equal, where they meet, they have the same z coordinate. So square root x squared plus y squared is equal to 2. All right, well, that just says this is x squared plus y squared equals 4 by squaring, right? So it's a circle of radius 2, or equals 2 squared is more suggestive. It's a circle of radius 2. Similarly, the circle here, if we put square root x squared plus y squared 1 and square both sides of the equation, we get x squared plus y squared equals 1 squared, is again a circle. This is a unit circle. And so what we have here for the region R, if we now sketch it in the xy plane, simple washer between the circles of radius 1 and radius 2. What does that suggest when we do this integral? I guess we ought to do it in polar coordinates, right? We're going to do the double integral over R of f here is y squared, and z, however, has to be replaced by what it is. So we put y squared z squared, but for z I have to put square root x squared plus y squared. So y squared z squared, ds becomes the square root of, this is your g of xy, the surface, partial of that with respect to x. This is actually a fairly important pair of partial derivatives here because they come up a lot in practice. All right, so if that's g of xy, then I want to compute the g dx is what? Well, if this is x squared plus y squared to the 1/2, I have 1/2 x squared plus y squared to the minus 1/2 times the partial derivative with respect to x is 2x, right? So it's the chain rule treating y as a constant. 1/2 function to the minus 1/2 times the partial derivative of the function with respect to x. Similarly, if you take partial derivative with respect to y, treating this as x squared plus y squared to the 1/2, well, you can see that dg dy is 1/2 x squared plus y squared to the minus 1/2 multiplied by 2y for the chain. So what that comes out to be then, well, I need just a little more room. Put this out. And say now this one is equal to 2 over 2 cancels, and you get x over square root x squared plus y squared. And this one, similarly, you get y over square root x squared plus y squared. Visible on the screen, I'm not sure. Looks like it just is, I think. Yeah. Okay. And so actually what you could have done on this one, because of the symmetry in x and y, you could have computed dg dx and then interchange x and y to get dg dy without any computation. So you can avoid this one together, just say by symmetry. This is the same thing with x and y interchange. So it's y over square root x squared plus y. All right, now I got it because I've got to put those into here. dg dx. See that line is getting a little small. Squared plus dg dy squared is y over square root x squared plus y squared. Squared plus 1 all under the square root dA. So equation 1 tells us if we have to do that. I guess I've got to erase this thing here. All right, so this is what we have to be able to evaluate to get the surface integral of this function, thought of as finding the mass of the surface. Well, let's see. This squared comes out nicely. X squared plus y squared. And then the square root is of x squared over x squared plus y squared. Plus y squared over x squared plus y squared. Now you can see these problems generally have to be cooked, all plus 1. And then dy and dx. Or, well, all right, let's just put dA for this stuff. In my other circle, and now observe that these added together are just 1. In general, what happens on these is you get something that's not easy to integrate, and you just wind up estimating this on the computer. But there's a few cooked problems in here, so we work through the details. And this is one, we get to square root 2 here. The whole thing is square root 2, double integral over the annulus r of x squared y squared plus y to the 4th. That's what we have to do. Well, let's see. Since it's an annulus, I want to switch to polar coordinates, right? It'll be easy constant endpoints in polar coordinates. R will go from 1 to 2 to go from the inside function to the outside. Think of this as a simple polar region, right? Theta goes from 0 all the way around to theta equals 2 pi. Inside curve is r equals 1, and the outside curve is r equals 2 in polar coordinates. So I can integrate r from 1 to 2 and theta from 0 to 2 pi to sweep out the annulus. Then I need all these in polar coordinates. So I've got r squared cosine squared theta, r squared sine squared theta, minus or plus r to the 4th sine squared, sine to the 4th, excuse me. R dr d theta. There's the integral I have to do. And now it's just a matter of evaluating integrals. I have a square root 2. And let's see, it's r to the 5th overall. Integral from 0 to 2 pi. Integral from 1 to 2. r to the fifth times sine squared times cosine squared plus sine squared by factoring dr d theta. A little bit of algebra. And now cosine squared plus sine squared is 1. So I can rewrite this as square root 2 integral from 0 to 2 pi. And now it's a function of theta times a function of r between the constant endpoints again. So I can just integrate sine squared theta d theta and times the integral from 1 to 2 of r to the fifth dr. Question so far, it's kind of complicated, but we can actually all get it on the whole board at once. Integrate sine squared theta, I'll use the half angle identity as the easiest way. Use reduction formula or something like that also. We'll call this 1 minus cosine 2 theta all over 2 by trigonometry. However, let's see. Yeah, okay. And we have square root 2 times the integral of 1 minus cosine 2 theta over 2 is theta minus a half sine 2 theta. And this multiplies r to the sixth over 6. Plug in 2 and 1 and take the difference. All right, well, sine 2 theta at 2 pi and 0 is 0, right? Because it's sine of 4 theta, sine of 4 pi, and sine of 0. So this one can be dropped out. So I've got here square root 2 times 2 pi over 2 is pi minus 0 from the other endpoint. And then this one is 2 to the sixth minus 1 to the sixth all over 6. Well, 2 to the sixth is 64, so this is 63 sixths. Which then amounts to 21 third, 21 halves times square root 2 gives us 21 square root 2 pi all over 2. Yeah. Okay. Comments on that one? There's how you actually evaluate a surface integral. As you use that theorem that says you can project it down to its domain in the xy plane, integrate the integrand with z replaced by what function it is on the surface. And generally you get a nasty integrand, but for a few cooked problems, we can actually do this.
So it's very similar to stuff we've already done.
Yeah.
That's good.
Yeah.
That's really
So
good.
this is an example of using the formula we got right at the end of this. And it's the same formula. All right, now what we want to do is contrast that with a vector surface integral. So they to integrate flux. Great.
The camera's blurry.
Hmm?
Camera was blurred.
Oh, yeah. I don't know what does that even. If it stays blurry, tell me again and I'll move the thing and it'll probably refocus. Okay now? We'll see. Somebody will scream if it's not.
Yeah.
All right, so we may wish to integrate f of x, y dot a unit normal vector. Why would we want to do that? This is actually, this kind of a thing. If you've got a vector field and a surface sigma, suppose F is this velocity field of a fluid or something, and so these are vectors from the velocity field coming out through the surface. Something. What you can do is consider normal to the surface, which is the normal to the tangent plane. And let's compute that unit normal. And if you take, should have looked perpendicular, it's not a good picture. And you might want to take, what's the velocity of fluid that's perpendicular to the surface? So you project this over onto here. And this one for a unit vector is F. Well, let's put it this way. The velocity component that's coming out through the surface is length of n, length of F, times the cosine of this angle theta between the surface and the normal, call that theta, or between F, the velocity field, and the normal, right, is the component of the velocity going out. So this is the velocity out at any point is F cosine theta, but that's equal to length of F times the length of the normal vector is just 1, the unit normal. So write that up there, equals unit normal to sigma times the cosine of the angle between, right? Because unit normal has length 1, but that is just F dot n, right? So what we want to integrate over the surface to see how much fluid is flowing out is to integrate this times the area of each piece, each parallelogram, if you will, to get the amount of fluid flowing out. So hence, surface integral of this F dot n use volume fluid flowing through surface, through sigma, per unit time, when F, I put F of X, Y, it can be a function of Z also. Put plus Z in here. When F of X, Y, Z is the velocity. Which is the double integral of the surface. Instead of putting in a scalar function, we put F dot n. F dot n is a scalar function because the dot product of the vectors is a scalar, right? So this replaces the little f, which we thought of as density, with F dot n, the dot product of the fluid velocity with the unit normal of the surface. So this will be, we can also call this for short F dot ds with a big S for surface instead of a little s for arc length over sigma. So we'll make this definition, and that will be the vector line integral, double integral F dot ds. I mean, double integral of the surface of F dot n ds, where this is the usual scalar surface. But now what is that? If we want to evaluate it, this is, and we pull the same trick we did with arc length. Some room up here. integral f dot ds. On the right, we can rewrite it as the double integral over R by the evaluation formula 1. To actually evaluate this, is f dot, and for the unit normal, I can compute it this way. What is a unit normal of the surface? I'm going to find out here in a second. But ds is square root of put it in here somewhere. Surface integral of f dot n over a surface sigma given by z equals g of x, y. And this is, we recall, dg dx squared plus dg dy squared plus 1 dA. So we replace ds with this and then integrate to the projection. And then all we need is the unit normal. So what is the unit normal? The unit normal, n, is any normal, capital N, divided by its length, right? Although we have to be careful now at this point, because when we do the surface integral, the normal could be up or down, and so this could be a unit normal upward through the surface or unit normal downward through the surface. Which one do we want? Well, let's use the unit upward normal by convention. When we write this, we'll say that n of the unit is upward normal. Then write that down here. And n is upward. Well, it doesn't mean straight upward. It wouldn't always be perpendicular to the surface, but it means it has positive z component as opposed to negative. So what is the unit upward normal? Here's how you can get it. If this is my surface, z equals g of x, y. This gets complicated here. You can think of this as parameterizing the surface. This projection down here. R. You increment x and y down here, partitioning this up. So you get rectangles down here. And that corresponds to curves here, plane, in the surface. And this curve might be holding y equals constant, right? It's over this y equals constant line here. So this is one of these things could be g of this one would be y arbitrary and x held fixed at some xk in the partition. And let's say xj. And y varies, and you sweep out this curve. Now, if x is fixed, then you've got a parametric curve. What g is z given as a function of one parameter y, so that y varies, you sweep out this curve. Then on this curve going this way, you hold y fixed, and you take z equals g of x yk. And so at the jkth point here, you have xj yk somewhere in the partition. You're taking a parametric curve this way, letting x vary. Parametric curve this way, and they intersect here, and then you have a tangent vector and a tangent vector to these. And the tangent to this curve is what? Take a tangent vector to a curve, you take the derivative, right? So you take the derivative of this with respect to the parameter x and treating y as a constant. And so this tangent vector is actually dg or dz dx at the point. Is the slope. And then the idea is let's call it dr dx is this tangent vector. R thought of as a function of one parameter x and y held constant. So it's dr dx of yk. Is that tangent vector. And then this one here holds x constant, and you take partial of r with respect to y with xj fixed. And then what is the cross product? It is the vector perpendicular to this, what you call this n, equals r dx cross dr dy. And from the picture, if you take dr dx cross dr dy, it's the upward normal. It always has positive z component. But what is that? Well, r is the vector this I should write it like this. This is this one ought to be dg dx 0, 1. The idea is have a so it's 1. Increment x by 1. The slope is dg dx. Well, that's the r dx. Looks like that, if you write the parametric equations correctly. And then dr dy, I'm sorry, this is dr dx. And this is crossed with dr dy, which is 0, 1 dg dy. So this is a vector tangent when you vary y and hold x constant. If you write g as a parametric function of y only, and that's if you write g as a parametric function of x holding y constant, then you get this tangent vector. So those are the two tangent vectors, dr dx and dr dy. And then when you take their cross product, what do you get? You get this times this, nothing, minus this times this is minus dg dx. And the second component is this times this, nothing, minus this times this is minus dg dy. Y. And then the third one is this times this, 1, minus this times this is 0. So this is the normal vector. Sorry, I'm really up this direction. I should have started at the top. N is then this vector minus dg dx minus dg dy 1. And so what we have here is we'll put that in here. Actually, let's put it in the next step. N over the length of n. So F dot NDS from here becomes F dot, the normal vector that's not a unit vector, it's this one, divided by its length, so this is N. And then DS is this. So find the vector surface integral by double integral F dot NDS, that scalar surface integral, and then write the unit upward normal as N divided by its length, where we compute it this way, the cross product of these two tangent vectors. And by convention, we define the surface integral to be the upward normal. And then we have this integral, because this is the ds of it, when you evaluate the surface integral. But now what is this? This is double integral over R, F dot, this vector, minus dg dx, minus dg dy, 1, divided by its length. Well, you root subsquare those and you get dg dx squared plus dg dy squared, and minus the quantity squared, right? Plus 1, but it's the same thing. And then times all this stuff. Square root of gdx squared plus dg dy squared plus 1 dA, and the square roots cancel. And so the vector surface integral just comes out to be the double integral over the region of projection, F dot minus dg dx minus dg dy 1 dA. That's how you can get it. You can evaluate it. This is the evaluation formula for F dot ds. It looks like that. Where for brevity, sometimes we like to write this as just capital N, not the unit normal, this upward normal, defined this way. Well, I wrote it here. So if you're wanting to think of this as evaluating a flux, an integral of F dot the unit normal ds, then you can evaluate it this way. And note, in a lot of textbooks, this vector surface integral is often called flux. F is a velocity field. We already talked about the flux through a curve when we were in 2 dimensions. This is the same concept in 3 dimensions. Instead of having the velocity flow per unit time through a curve in the plane, now we've got velocity fluid volume per unit time through a surface. Or as area through a curve, now it's volume through a surface. So you write it with this notation, phi, capital Phi, is double integral F dot ds. Now finally we get to calculate it. But as you can see, in some sense, this is actually easier, right? Because before in the surface integral, you had to evaluate this integral of a square root of a mass, and that generally is hard. The square root's gone because it canceled here. And so when you're actually calculating a flux, instead of just a surface integral of a general function, that nasty square root falls out. So we can call this 2, this is the evaluation formula. That was the definition over there. This is the evaluation formula. If you don't have a square root, it's easier. There is one disclaimer in here too. We made an assumption here throughout that Z is a function of X and Y, and we need for this an orientable surface in addition to our other requirements. Orientable means that we can orient the vectors to change continuously orient the normals, I'm sorry, orient N normals to change continuously while being on one side of the surface. So for instance, this isn't a problem if you just put Z equals F of X, Y. But if we want to do this more generally, you can have the following kind of setup. The book gives a nice illustration of this, but it's always better if you see it in person. So you can take a strip of paper, I guess I can see it. And I cut a few here. And you can take a piece of tape now. And if I take the piece of paper like this, it's orientable because I can make my vectors come out this outside all the way around and change continuously if it's a closed surface, a more general surface than just Z equals F of X, Y. And so that's an orientable surface like that. Maybe we should tape this one together just for a basic example. And it has a nice property. Stuck my finger. All right. There we go. I can't do it. Back to kindergarten. All right. So there's an orientable surface, and it has a nice property that I can take this marker and draw a line way around it. And it's just got one side, right? The line is just on the outside. You can say there's an outside and an inside. But if you take this thing and give it a half twist like that and then close it up, then we have what's called a Mobius strip. It has an interesting property. That I can take a line and draw it around. And again, I eventually get back to where I started from. Get this a little better. But as I go around, I notice this thing actually only has one side. I go back to the beginning, there isn't any spot along the paper that's not marked in the middle. I'm just continuing to draw all the way around. And everywhere, there's a line down the middle, there's only one side to this surface, and it's not orientable. If I start with the vectors pointing out on this side and go all the way around, they'll be pointing on the inside when I come back the other way, and so there's no way to make these continuously change and point to one side of, so there's one side of the surface. Two sides of the surface, there's only one side. And they have the interesting property, of course, this one you know what's gonna happen, right? If I cut this loop along the line, then it turns into two loops at half the width, but if I take the movie strip, try and cut it down the middle. Back where I started, hopefully. Oh, it's only one circle. That's- so it divides into a single loop of twice as long. And if you give it a full twist, then it turns into two places again, but if you put a twist and a half, and it gives you this kind of thing again. And it comes out, and you can try cutting it again and again, but it always comes out to be one loop twice as long. So these non-orientable surfaces have fun properties, topologically. So when you start to extend this to closed surfaces, you have to stick to orientable surfaces. And even with these things, if you twist them around so that you don't have just an upward normal all the time like that, you can run into problems. All right. So the example is, look it up online for fun, the most strip. It's a piece of paper with a half twist in it. There's a picture in the notes. Let's see if I can do an example here. Um, from my notes, that's what pull this back down again, sorry. Oops. Come on in a second. All right, so there's my picture of the Mobius strip. You can see it on the camera. Just a paper with a half twist. And there's the unit normal. There we go. Okay. So let's look at this one. Suppose I want to evaluate the flux of the vector field where the F just points straight up, 0, 0, Z. So it's fluid pointing, pushing straight up, equal to the value of Z above the XY plane. And suppose we push it through the circular paraboloid, Z equals 4 minus X squared minus Y squared over the XY plane, just have coarseness over the XY. And oh, and that's for one example, and then we can do the same thing through the hemisphere. Half of a sphere of radius 2. We can calculate the flux through either one of those surfaces. So if you look at the domain of the surface Z equals 4 minus X squared minus Y squared, the circular paraboloid, 4Z greater than or equal to 0. Well, you want to intersect it with the plane Z equals 0 where you're cutting it off. If you put in Z equals 0, you get 0 equals 4 minus X squared minus Y squared, which is a circle of radius 2. So the domain of the paraboloid is the disk X squared plus Y squared less than or equal to 4. We can draw it over on the board in a minute. And by the calculation formula, then we'll say that we just wrote the integral F dot ds is just double integral F dot ds over the surface. Sigma is the double integral F dot the upward normal over the region of projection, which was the disk of radius 2. So if we want to integrate dz dx, so here's F was the vector field 0, 0, Z, and we have to replace Z with what the surface is, square root 4 this one, 4 minus X squared minus Y squared. I was looking at the wrong one. So we replace Z with 4 minus X squared minus Y squared. Here is the velocity field, 0, 0, Z. And we dot product that with, for the surface, dz dx, derivative d with respect to x is minus 2x, dz dy is minus 2y, and 1, right? So dz dx, dz dy, 1, or dg dx, dg dy, 1. And then the velocity field dot product, and we'll take the integral over the region of projection of that dot product. So you compute 0 plus 0 plus 4 minus X squared minus Y squared is the dot product. Case here. I just have to integrate that over the disk. Well, the disk radius 2, r goes from 0 to 2, theta from 0 to 2 pi, and I put r dr d theta. Integrate this in polar coordinates. This is 4 minus r squared. So it simplifies like that. And then you can evaluate this double integral. So that is the flux through the paraboloid, circular paraboloid. Then I've got it below. For the hemisphere, if I now calculate the flux through the hemisphere, I've got well, tell you what, this one I used a parametric representation. Let me not write this one yet. Let's just do the other one. Write that a little more detail. I told you this is a complicated part of the course. It's not so terribly difficult, but it's so complicated. Here's the example then. Flux through the surface sigma given by z equals 4 minus x squared minus y squared. With the restriction that z has to be non-negative. Of the vector field f of x, y, z equals 0I, 0j plus zk. Is the integral of the surface f dot n. Yes. dA, well, f dot ds for the first notation over sigma. Then becomes the double integral of the region of projection of f dot n dA to evaluate by 2. Evaluation formula for the vector surface integral. All right, now f is zk, so it's just, oh, I need to replace z with what it is on the surface. It's 4 minus x squared plus y squared, k. That'll be f. And then dot the unit normal vector minus dg dx I minus dg dy j plus k upward normal dA over the region of projection. Now, what's the region of projection? We have to draw the picture. Here's how you can sketch this picture. Z equals 4 minus x squared minus y squared. We've mentioned something like this before. You first think of z equals x squared plus y squared, right? We know that is x squared over 1 squared plus y squared over 1 squared is a circular paraboloid opening up with vertex at the origin, right? That's one of the ones we memorized from quadratic surfaces. So it looks like that. Now, if we turn it upside down, we take z equals minus x squared minus y squared, right? Is the same thing going downward, looks like that. And z equals 4 minus x squared minus y squared, then slides it up 4 units. So that it's up here. We know it looks something like this. Since it has circular cross sections, right, it's a circular paraboloid, A equals B, A equals 1, B equals 1. This will intersect the XY plane in a circle. So this is the one we're interested in. It's this surface right here. And we want to find the flux through that surface. We can integrate over the region R, that's the projection. This is this disk down here. And then this up here is the surface sigma. So we project sigma down on the bar here. And n, the normal to the surface at any point, is then that vector there. All right, so what is the region R? We said we intersect it with the plane z equals 0 to get this position. So where they intersect, these two are equal, and you get from these 0 equals 4 minus x squared plus y squared intersection in the xy plane. Well, that's just x squared plus y squared equals 4. That's the boundary, the circle here, right? So then the disk runs over the interior of that boundary, write this as double integral. Theta going from 0 to 2 pi, r going from 0 to 2 to run over the disk. Uh, 4 minus x squared minus y squared can be rewritten as 4 minus r squared. Oh, and I didn't dot product these yet. The dot product is just this, and this is 0 times this plus 0 times this plus 1 times this. So the whole thing here, the dot product is just 4 minus x squared minus y squared by the dot product, which is also 4 minus r squared. So then I can put in this integrand 4 minus r squared, the dot product, and then take dA as r dr. And that will then evaluate the volume of fluid per unit time going through the circular paraboloid that we see there, portion of it. Well, there's no theta in here, so I can pull the d theta through and say this is integral from 0 to 2 pi d theta, integral from 0 to 2 of 4r minus r cubed dr, and hopefully it comes out to be the answer on the board there. 2 pi times 2r squared minus r cubed over 3, plug in 0. Let's say that's 8 minus 8 thirds is 16 thirds. I should get 32 pi over 3, it looks like. I got 8 pi, didn't I?
Shouldn't it be r to the fourth divided by 4?
Yeah, I can't integrate. All right, part of the 4th over 4. Thank you. Maybe we'll get a 4th over 4. So now I get 8 here minus 4. It's 4. Yep, good. Now it works. Thank you. Look at that. Murphy's law didn't apply. It's in the last step instead of the first one. All right. 8 pi. So there's surface integrals and vectors, scalar surface integrals and vector surface integrals. And the vector ones are actually easier because you get that square root out.
Can you move the camera a little bit?
Yeah. I should move that over to that. Is that enough? I think. Well, now, if that's not enough, and sometimes these are very difficult to evaluate, we can add one more bits to this. Remember, beautiful Green's theorem, we could take a single integral and if we could evaluate, we could turn it into a double integral. It's not like it's going to be harder, right? But actually for some nice regions, it was actually easier to do the double integral of an integral instead of a single integral. You know, if it was a nice region, it kept you like it was a square, instead of integrating around the curve in 4 pieces, we could just integrate once over the square that's inside, and that could be easier kind of thing. We can do the same thing now with these double integrals. We can turn them into triple integrals. How about that? So for those of you that are masochists, this is the one for you. This is the divergence theorem. We won't try and prove this one for lack of time. Divergence theorem of the great Gauss, right? Everybody's heard of Gauss, the prince of mathematics, and one of the 3 greatest mathematicians of all time. Last guy who probably understood all of mathematics in the whole day. Now we just all specialize in some little corner of it. The divergence theorem that says under nice conditions, meaning that you have to have continuous partial derivatives of everything and a continuous integrand. So for a surface with continuous partials and it's orientable and the function you put in the integrand has to be continuous. So under nice conditions of the last theorem, plus orientable, We have another way of evaluating F dot ds, surface sigma. It can actually be done as the triple integral over, I guess the book calls it G, of the divergence of F. Remember, we did divergence and said, what are we ever going to do with that? Now we finally get it. So we can take the divergence of F over the volume where, I'm going to put a circle here, meaning it's a closed surface. Sigma is the boundary surface to solid G. There's the divergence theorem of Gauss. So sometimes this actually makes it a little easier to turn a double integral into a triple integral, particularly if what you have is a big cube or a big sphere. Those are nice and easy things to integrate over solids. So here's the statement of the theorem. Put it all in one place. What we mean by nice and so forth. Let's say maybe a closed, smooth, oriented surface in three-dimensional space. That's what R3 means. It's X, Y, Z rectangular coordinates. With outward normals, just put that on there. It has to be outward normal. Bounding a solid W. You might write that in the theorem here. And it's outward. And then this is your I, J, K here. Just use the other notation. And with continuous first partial derivatives and an open set containing a solid W, then the surface integral is equal to the divergence of F over the volume. So there's the proof down there with lots of gory detail. It's also in the book, I think. Here's the example. All right. Suppose I'm going to calculate the flux of this velocity field out of a rectangular parallel python, which is a rectangular box, x going from 0 to 2, y going from 0 to 4, z going from 0 to 1. Well, it's easier, instead of integrating over the 6 faces of this box, the surface integral on 6 different sides and trying to add them all together. What a mess, right? To just do one integral, one triple integral over the solid where you go between these constant endpoints, right? So box is the ideal thing to do this with. And so we'll say by the divergence theorem, the double integral over the surface of this F is equal to the triple integral of F over the box that has those limits. But the divergence is what? The divergence is just del dot F. So you take ddx of this plus ddy of this plus ddz of this is the divergence. ddx of this is just 2x. dy of this is 0, and ddz of this is x. So you get 2x plus x is 3x over the volume. All I have to do is do the integral x going from 0 to 2 on the inside, y going from 0 to 4, and z going from 0 to 1 runs me over a rectangular box of 3x, the integrand, dx, dy, dz. And since my endpoints are constant, the integrand is a product of functions of x times function of y times function of z. I just break it up into the product of 3 integrals. Integral of 3x is just 3x squared over 2, plug in the endpoints. And then this one's just 4, and this one's just 1, and it all multiplies out to 24. There's the volume of fluid per unit time flowing out of this rectangular box through this velocity field. we're not gonna do this one. I'm not gonna cover all the notes. There's a bunch in there on, about various things, the second form of Green's theorem and so forth. Admit that, you don't have to look at all the notes. I'm just using some examples out of here. All right, so let's make the last thing tonight then to. That's right. To do that example on the board. Really should put that picture up there. That example would look a lot better. Suppose you have this field, f of x, y, z. Vector field is x squared minus y squared, z squared. XC. And your surface sigma is the box. 0 to 2, 0 to 4, and 0 to 1. Up to 4. Box right there. So sigma bounds the thing, and the solid itself is called G. And if I want to find the flux through the closed surface, sigma, this velocity field, we can say, oh, we can just integrate that by taking the triple integral by divergence theorem over the solid that encloses G of the divergence of F. And then the divergence del dot F was ddx of the first component plus ddy of the second component plus ddz of the third component. It's out to be 2x plus 0 plus x is 3x. Take the triple integral, since it's over a box, it's very easy. X goes from 0 to 2, y goes from 0 to 4, z goes from 0 to 1, 3x, dx, dy, z is that volume integral. And if you get something on the final, it'll be easy like this. A box that you do in rectangular coordinates or a sphere that you do in spherical coordinates, one of those two kind of things. Otherwise, it takes too long, and I probably will get it wrong myself. This breaks up into the product of three integrals. We said integral from 0 to 1 dz, integral from 0 to 4 dy, 3 that can come out, and then integral from 0 to 2 x dx. 3 times 1 times 4 times x squared over 2 evaluated at 0 and 2 gives me 2. 3 times 4 times 2 then gives me 20. Half the time these things are so long I get the wrong answer. I gotta check them. All right. Any comments on that one? This is an alternative when it happens to be over a closed orientable surface. Then you can say there's an inside and outside, and you can integrate over the volume and inside the divergence. All right, well, with that, it's time to go. I keep looking at that clock. I started a minute late because that clock was slow, and I'm finishing a minute late for the same reason. So let's see, I've got some problems here. Take a look at 15.7 on the divergence theorem. 1, 3, and 11. I don't want to do anything fancy. I'll just give you problems. Yeah, let's just do that. Instead of saying over a box or a So here, let's say if you like one of these, I'll give you one of these with different numbers. On Monday, I anticipate around that time putting on a set of problems to study for the final exam. On Monday, we'll do Stokes' theorem, which is the last crowning glory for the theorem. Divergence theorem and Stokes' theorem sort of pull everything together for the course. We'll finish on Monday and review on Wednesday. So look forward to seeing you then.
Explain the bounds in the last part with 3x, like those 0 to 1, 0 to 4. Like, how'd you get those bounds
Oh,
again?
from the blocks, I'm just saying, if I integrate over the solid, x goes from 0 to 2, y from 0 to 4, and z from 0 to 1. Yeah. It was just given in the problem, that's all. I wish everybody a good night then.